Here is today's problem. We want to solve the equation x cubed minus x squared equals 100. Here x cubed means x times x multiplied out in full, and x squared means x times x, the same number taken twice. On the right side sits the plain number 100, our target. We are looking for every value of x that makes the two sides equal. Let us start by putting the equation into a friendlier shape. The first step is to bring every term over to one side. We subtract 100 from both sides of the equation. Subtracting the same amount from both sides keeps the balance. The equation keeps the same solutions after this move. On the right, 100 minus 100 leaves us with 0. That gives x cubed minus x squared minus 100 equals 0. Now the entire expression on the left is set equal to 0. Having 0 alone on one side sets the stage for factoring. On the left we now have a cubic, a polynomial of degree 3. Our plan is to break this cubic apart into simpler factors. Factoring trades one big equation for a few small ones. To get the factoring started, we first search for a single root. A root is a value of x that makes the whole polynomial equal 0. For this search, we lean on the rational root theorem. Our cubic has whole number coefficients, so the theorem applies. The theorem describes every rational number that could be a root. Imagine a possible root written as a fraction in lowest terms. The theorem says the top must divide the constant term, and the bottom of the fraction must divide the leading coefficient. In our polynomial, the constant term is minus 100. Its divisors are exactly the same as the divisors of 100. The leading coefficient, the number in front of x cubed, is 1. So the bottom of any candidate fraction has to divide 1. That forces the bottom to be 1, so every candidate is a whole number. And that whole number has to divide 100 with no remainder. So our full candidate list is simply the divisors of 100. Divisors are the numbers that fit into 100 with nothing left over. The positive ones are 1, 2, 4, 5, 10, 20, 25, 50, and 100. Each of these also brings along a negative partner. A number like 3 never appears, since 3 does not divide 100. These are the only rational numbers that could possibly be roots. We can settle all of the negative candidates in one stroke. Suppose for a moment that x were some negative number. Then x cubed is negative, since 3 negative factors give a negative. Meanwhile x squared is positive, so minus x squared is negative. Negative plus negative stays negative, whatever the sizes are. But a solution must make x cubed minus x squared equal to 100. A negative total can never equal the positive number 100, so every negative candidate is ruled out in a single step. Only the 9 positive divisors are left for us to test. To test a candidate, we plug it into x cubed minus x squared. If the output is exactly 100, that candidate solves the equation. We begin with the smallest candidate on the list, x equals 1. 1 cubed is 1, and 1 squared is 1 as well. So the expression gives 1 minus 1, which comes out to 0. 0 is a long way from 100, so we cross off 1 and move on. The next candidate up the list is x equals 2. 2 cubed is 8, since 2 times 2 equals 8. 2 squared is 4, and 8 minus 4 leaves us with only 4. That is still nowhere near 100, so we cross off the 2 as well. We continue upward with the next candidate, x equals 4. 4 cubed is 64, because 4 times 4 is 16, and 16 times 4 is 64. 4 squared is 16, so we compute 64 minus 16 and get 48. 48 sits closer to the goal, but it still falls short of 100, so we move one step further and test x equals 5. 5 cubed is 5 times 5 times 5, so 25 times 5, which is 125. 5 squared is 25, so the expression reads 125 minus 25. 125 minus 25 comes out to exactly 100, right on the mark. So x equals 5 satisfies the original equation perfectly. We have found our first solution, x equals 5. The value 5 turns the polynomial into 0, exactly as a root should. A polynomial of degree 3 can have as many as 3 roots, so the equation might still be holding on to other solutions. The candidates we never reached were 10, 20, 25, 50, and 100. Instead of plugging in each one, we can factor the cubic. The factored form will judge all of them in a single move. It will also expose any roots that are not whole numbers. This is where the factor theorem comes into play for us. Since 5 is a root, x minus 5 must divide the cubic evenly. So we divide x cubed minus x squared minus 100 by x minus 5. We will use long division, just like long division with numbers. Our cubic is missing a plain x term in the middle, so we rewrite it with a placeholder term, plus 0x. Nothing about the polynomial changes, since 0x is just 0. The dividend becomes x cubed minus x squared plus 0x minus 100. The placeholder keeps every column of the division lined up. Long division here works one power of x at a time. First we ask how many times x fits into x cubed. X cubed divided by x is x squared, our first quotient term. Now we multiply x squared by the divisor, x minus 5. That product comes out as x cubed minus 5x squared. We subtract this product from the matching terms above it. X cubed minus x cubed cancels away completely to nothing. Then we handle minus x squared minus negative 5x squared. Subtracting negative 5x squared is the same as adding 5x squared. So minus x squared plus 5x squared leaves positive for x squared. Next we bring down the placeholder term, plus 0x. Our new working line reads for x squared plus 0x. We divide for x squared by x and obtain for x for the quotient. So far the quotient we are building reads x squared plus for x. Multiplying for x by x minus 5 gives for x squared minus 20x. We subtract, and the 4x squared terms cancel each other. Then 0x minus negative 20x becomes positive 20x. We bring down the final term of the dividend, minus 100. The bottom line of our division now reads 20x minus 100. Dividing 20x by x gives 20, the last term of the quotient. We multiply 20 by x minus 5 and get exactly 20x minus 100. Subtracting one line from the other wipes out every term. The remainder of the whole division is exactly 0. A remainder of 0 confirms that x minus 5 divides cleanly, and the quotient we have collected is x squared plus 4 by plus 20. So the cubic splits into x minus 5 times x squared plus 4x plus 20. Let us expand this product once and see that it matches. X times the bracket gives x cubed plus 4x squared plus 20x. Minus 5 times the bracket gives minus 5x squared minus 20 by minus 100. Now we add these two rows of terms together column by column. For x squared minus 5x squared combines into minus x squared. 20x minus 20x cancels, while the minus 100 remains. So the expansion returns x cubed minus x squared minus 100. That is precisely our polynomial, so the factorization is correct. Our equation now says this product of two factors equals 0. A product is 0 exactly when at least one of its factors is 0. This principle is what makes the factored form so useful. So we take each factor in turn and set it equal to 0. The first factor gives the equation x minus 5 equals 0. Adding 5 to both sides, we find x equals 5 once again. That matches the solution we discovered earlier by testing. The second factor gives x squared plus 4x plus 20 equals 0. This is a quadratic, and we solve it by completing the square. Its x squared term has coefficient 1, so no dividing is needed. Completing the square rewrites it so x appears only once. We focus on the first two terms, x squared plus 4x. We take the coefficient 4, cut it in half, and square the result. Half of 4 is 2, and squaring that 2 produces 4. So x squared plus 4x equals x plus 2, all squared, minus 4. We substitute this back into the quadratic equation. It becomes x plus 2, all squared, minus 4 plus 20 equals 0. The loose numbers, minus 4 plus 20, combine into plus 16. So the equation reads x plus 2, all squared, plus 16 equals 0. Moving the 16 across, x plus 2, all squared, equals minus 16. But the square of a real number is never negative, so this factor contributes no real solutions. That leaves x equals 5 as the only solution of the equation. Every root of the cubic had to come from one of those two factors, so the solution set of our equation is the single value 5. In other words, x equals 5, and no other number gets the job done. To finish, we verify the solution inside the original equation. We substitute x equals 5 into x cubed minus x squared. That means computing 5 cubed and 5 squared separately first. 5 cubed means 5 times 5 times 5, taken one product at a time. 5 times 5 is 25, and then 25 times 5 is 125. Next, 5 squared is simply 5 times 5, which is 25. So the left side of the equation becomes 125 minus 25. 125 minus 25 equals 100, the exact number on the right side. So substituting 5 for x turns the equation into 100 equals 100. Both sides agree, and the solution is confirmed. We can also test it inside the factored version of the cubic. With x equals 5, the factor x minus 5 becomes 5 minus 5, so 0. The other bracket becomes 25 plus 20 plus 20, which is 65. And 0 times 65 is 0, matching the rearranged equation. So the check succeeds in the factored form as well. Everything fits together, and the problem is solved. So the final answer to today's problem is x equals 5. Thank you so much for watching all the way to the end. If this solution was helpful, a like on the video is appreciated, and subscribing to the channel means catching the next problem too.